Artificial intelligence can fail silently through a hidden problem. This problem is called overfitting and affects many models. Overfitting happens when AI memorizes instead of truly learning patterns. Many beginners confuse high accuracy with real model intelligence, but high accuracy can sometimes hide serious underlying issues. A model may perform perfectly during training, but fail later. This failure usually appears when testing on new data. Overfitting is one of the most important machine learning challenges. It quietly reduces real-world performance of advanced AI systems. Imagine a student who memorizes answers without understanding concepts. That student performs well only on familiar questions repeatedly, but struggles badly when new questions appear unexpectedly. AI behaves in exactly the same way during overfitting. Instead of learning patterns, it memorizes training examples directly. This creates an illusion of intelligence during evaluation stages. Developers often discover overfitting after deployment in real environments. Training data becomes too familiar to the learning model. The model starts treating noise as if it were pattern. Even random details get stored as meaningful information incorrectly. This leads to poor generalization on unseen future data. Generalization is the real goal of every AI system. Without generalization, AI cannot perform reliably in real world. Overfitting breaks the balance between learning and memorization completely. Simple models often avoid overfitting better than complex ones. However, too simple models may underperform on difficult tasks. Finding balance is key in machine learning. Model design. Overfitting usually appears when training continues for too long. The model keeps improving training accuracy without real improvement. Validation. Accuracy starts decreasing while training accuracy keeps rising. This gap is a major warning sign of overfitting. Many engineers monitor this gap during model training carefully. Large datasets help reduce chances of overfitting significantly over time. More diverse examples. Force models to learn general patterns. Limited data makes models memorize instead of understanding relationships. Noise in data also contributes heavily to overfitting problems. AI systems cannot easily distinguish noise from real signals. This confusion leads to incorrect learning of false patterns. Overfitting is especially common in deep learning models. Today, deep networks have millions of parameters that memorize easily. Each parameter can store small details from training data. This creates extremely precise but fragile learned representations. Such models break easily when exposed to new situations. Overfitting reduces trust in AI systems used in real life. Self-driving cars must avoid overfitting to ensure safety. Medical AI systems also require strong generalization capabilities. Always. Overfitting in healthcare could lead to dangerous misdiagnosis errors. Financial prediction models also suffer from overfitting frequently observed. These systems may predict past data perfectly, but fail. Future real-world success depends on avoiding memorization-based learning. Machine learning engineers constantly fight overfitting during model development cycles. Regular evaluation helps detect early signs of overfitting issues. Training and testing datasets must remain clearly separated, always. Mixing datasets can hide overfitting problems during evaluation stages. Overfitting becomes visible when real-world performance drops suddenly. Many AI failures are actually caused by overfitting silently. Understanding this concept is essential for every AI developer. Even advanced models can suffer from overfitting without warning. The problem becomes worse with small or biased datasets. Biased data causes models to learn incorrect patterns strongly. Overfitting is not a bug, but a learning imbalance. It represents too much focus on training data specifics. True intelligence requires understanding beyond memorized examples. Only AI must learn patterns that apply in multiple situations. Overfitting prevents AI from adapting to new environments properly. This makes models rigid instead of flexible and adaptive. Flexibility is essential for real-world artificial intelligence systems. Without it, AI remains trapped in training environment limitations. Developers use many techniques to control overfitting during training. These techniques improve generalization and reduce memorization risk. Overfitting detection is a critical step in AI development pipeline. Ignoring it leads to unreliable and fragile AI systems. Many successful models are carefully tuned to avoid overfitting happens due to imbalance between data and model complexity. When models are too complex, they easily memorize training patterns. Simpler datasets increase risk of memorization instead of learning. Machine learning models learn by minimizing error during training. But minimizing training error does not guarantee real-world success. Overfitting begins when model starts capturing noise as signal. Noise refers to random, meaningless variations in training data. AI struggles to separate noise from useful information patterns. Large models with many parameters tend to overfit easily. Each parameter adjusts to small details in training examples. These details may not exist in real-world data. As training continues, model becomes more specialized to dataset. Specialization reduces flexibility when facing unseen data distributions. Data distribution mismatch increases chances of overfitting significantly. When test data differs, model performance drops rapidly. This gap is known as generalization gap in AI. Generalization gap measures difference between training and testing accuracy. Larger gaps indicate stronger overfitting inside the model. Small datasets force models to memorize limited examples. Repetition leads to overfitting even in simple algorithms. Noisy labels in datasets increase confusion during training process. Incorrect labels mislead model into learning false relationships. This creates long-term damage to model understanding ability. Overfitting also depends on number of training epochs used. More epochs allow model to memorize deeper patterns. Slowly, early stages of training usually show good generalization behavior. Later stages often cause overfitting if training continues excessively. Validation loss helps identify overfitting during model training process. When validation loss increases, overfitting is likely occurring strongly. Training loss decreasing while validation loss rising is warning. This opposite movement indicates model memorizing training dataset details. Deep neural networks are especially vulnerable to overfitting problems. Their multiple layers allow complex feature extraction easily. However, excessive complexity reduces ability to generalize effectively. Overparameterization is a major cause of overfitting in deep learning. Overparameterized models have more parameters than necessary required. These extra parameters store unnecessary patterns from data. Feature correlation can also lead to overfitting issues. Highly correlated features confuse model learning process significantly. Model may assign incorrect importance to irrelevant features. This reduces accuracy when facing real-world inputs. Overfitting is also influenced by lack of data. Augmentation. Data augmentation increases diversity of training examples artificially. Without augmentation, model sees limited variations during training. Limited variation strengthens memorization instead of general pattern learning. Regularization techniques help control overfitting in machine learning systems. These techniques penalize overly complex models during training. Penalization forces model to simplify learned representations internally. L1 and L2, regularization, are commonly used methods. Dropout randomly disables neurons during neural network training. This prevents model from relying on specific pathways. It forces network to learn redundant representations. Effectively, ensemble methods also reduce overfitting by combining multiple models. Different models compensate for each other's weaknesses. Effectively bagging is one common ensemble technique used widely. It trains multiple models on different data subsets. Final prediction becomes average of all model outputs. This reduces variance and improves generalization performance significantly. Cross-validation helps detect overfitting during evaluation stage. It splits data into multiple training and testing sets. Results are averaged to ensure robust performance estimation. Overfitting often appears when model learns dataset-specific noise. Such noise does not represent true underlying patterns. Real-world data is usually more complex and varied. Training data cannot capture all possible real-world variations. This limitation makes overfitting a natural machine learning risk, (MEDAL). Bias and variance trade-off plays an important role here. High variance models are more prone to overfitting issues. Reducing variance improves generalization, but may increase bias. Balancing bias and variance is key to good models. Overfitting is worse when dataset is highly imbalanced. Minority class patterns get memorized instead of generalized properly. This leads to poor.
Overfitting has caused many real-world AI system failures. Some early AI models worked well only in labs, but they failed dramatically when deployed in real environments. Self-driving cars have faced overfitting-related safety challenges. Models trained in limited conditions struggle in new environments. Weather changes often expose weaknesses in overfitted perception systems. Medical AI systems can misdiagnose due to overfitting issues. Training on limited hospital data reduces generalization ability significantly. Financial prediction models often fail during unexpected market changes. Overfitted models perform well on historical but not future data. Stock market is highly dynamic and unpredictable environment. AI trained on past patterns struggles with new trends. Facial recognition systems also suffer from dataset bias overfitting. Limited demographic data causes poor real-world accuracy performance. Surveillance systems may misidentify individuals due to overfitting errors. Speech recognition models can fail with different accents. Training data bias leads to poor performance across regions. Overfitting increases risk in critical decision-making systems globally. Many AI failures are not algorithm bugs, but data issues. Poor data quality often leads directly to overfitting problems. Companies invest heavily in preventing overfitting before product launch. Model validation in real environments is a crucial step always. Simulation testing helps reduce risk of overfitting deployment failure. AI in autonomous drones must generalize across unpredictable conditions. Overfitted navigation models can crash in unseen terrain scenarios. Robotic systems require strong generalization for safe operation environments. Overfitting can make robots overly dependent on training environments. Chatbots trained on limited conversations may respond incorrectly. Natural language models also suffer from dataset overspecialization issues. Overfitting reduces creativity and flexibility in AI responses. General-purpose AI must avoid memorizing specific training dialogues. Language models improve through diverse and large-scale datasets. Internet-scale data helps reduce overfitting significantly in models. However, noisy internet data also introduces new challenges. Balancing noise and information is critical AI development skill. Overfitting is more dangerous in high-stakes AI systems. Wrong prediction in healthcare can lead to serious consequences. Autonomous driving errors can cause physical real-world harm. Financial AI errors can lead to massive economic losses. Therefore, overfitting control is essential in regulated industries. Tech companies use strict testing to detect overfitting early. Model audits help ensure fairness and generalization quality. Real-world benchmarks are more important than training accuracy. Competitive AI models focus on validation performance, not memorization. Kaggle competitions often reveal overfitting in participant models. Winning models usually use strong regularization techniques. Data leakage is another cause of hidden overfitting problems. Leakage happens when test data influences training process accidentally. This creates falsely high performance during evaluation stages. Proper dataset separation is critical to avoid leakage issues. AI researchers continuously improve methods to reduce overfitting risk. New architectures include built-in regularization mechanisms. Transformers use large-scale data to improve generalization. Pre-training on massive datasets reduces dependency on small data. Fine-tuning adapts generalized knowledge to specific tasks. Transfer learning is a powerful solution against overfitting challenges. Industry increasingly relies on pre-trained foundation models today. These models show better robustness across multiple domains. Overfitting research continues to evolve in machine learning field. Scientists explore better loss functions to improve generalization. Optimization techniques also influence model overfitting behavior significantly. Stochastic training methods help reduce memorization tendencies. Randomness in training improves model adaptability over time. Dropout layers remain widely used in deep learning. Ensemble AI systems dominate high-performance applications today.
Overfitting teaches us intelligence is not just memorization ability. True AI must generalize beyond scene training experiences completely. The difference between intelligence and memory defines machine learning. Overfitting represents failure of abstraction in artificial systems. Machines must learn concepts, not just specific examples, only. Human intelligence naturally avoids strict memorization. In most cases, AI struggles when data patterns become too specific. Structured. Generalization is ultimate goal of every intelligent system. Design. Overfitting shows limits of current machine learning approaches. Clearly, even advanced models can fail without proper data balance. Data diversity is foundation of intelligent system performance quality. Without diversity, models become fragile and overly specialized systems. Robust AI requires exposure to unpredictable real-world data. Real environments are far more complex than training datasets. This complexity exposes weaknesses in overfitted machine learning models. Intelligence emerges from adaptability, not from perfect memorization skills. Overfitting reminds us, learning is about patterns, not details. Machine learning models must extract essence of information effectively. Simplicity often leads to better generalization in real systems. Complexity without control leads to fragile AI behavior patterns. Overfitting is a reminder that perfection on training is meaningless. Real success depends on performance in unseen situations. Always. AI evaluation must prioritize generalization over training. Accuracy results. Training. Accuracy alone can be misleading. Performance indicator metric. Validation and testing. Define true capability of AI systems. Overfitting challenges. Push researchers toward better learning algorithms constantly. Every new technique aims to improve generalization performance stability. Artificial intelligence evolves through solving overfitting and bias problems. Better datasets lead to better and safer AI outcomes. Ethical AI design requires careful attention to overfitting risks. Poor generalization can cause real harm in society systems. Responsible AI development includes strong testing and validation phases. Overfitting is central concept in machine learning. Education worldwide. Students learning AI must deeply understand this phenomenon. Clearly, without this understanding, models are likely to fail. Often, overfitting connects theory with real-world machine learning practice. It highlights importance of balance between bias and variance. Good models achieve equilibrium between simplicity and complexity. Effectively, overfitting shows importance of continuous learning in AI systems. Models must evolve as new data becomes available continuously. Static intelligence cannot survive in dynamic real-world environments. Adaptability is a key trait of successful artificial intelligence systems. Overfitting teaches importance of continuous improvement and refinement process. Machine learning is never finished, but always evolving discipline. Data-driven systems require constant updates and monitoring. Always overfitting risk increases when systems are left unchecked. Long-term. Monitoring ensures models stay relevant and accurate over time. AI maintenance is as important as initial model training. Overfitting is not failure, but signal for improvement needed. It shows where learning process needs better adjustment strategies. Every overfitted model provides insight into training. Weaknesses present. Debugging. Overfitting improves overall system understanding and design quality. Machine learning. Success depends on handling. Overfitting effectively. Always. Strong models are built through careful balance of learning. Overfitting prevention leads to stable and reliable intelligent systems. These systems can operate safely in unpredictable environments. Real intelligence requires flexibility across changing conditions. Constantly, overfitting reduction improves trust in artificial intelligence applications globally. Trust is essential for adoption of AI technologies widely. Without trust, AI cannot be integrated into society effectively. Overfitting undermines trust by creating unreliable predictions in systems. Solving. Overfitting increases confidence in machine learning outcomes significantly. Future AI research focuses heavily on generalization improvements continuously. New architectures aim to reduce memorization tendencies. Auto